Recording. Okay, welcome everybody to this month's Ithaca Fest. Today we have Matteo Capucci from the University of Strathclyde, who's going to talk about triple categories. So not tri-categories, triple categories. So like double categories, but triple of open cybernetic system. And please, Matteo, welcome and take it away.
Hi everyone. Thank you very much for inviting me here. It's really a pleasure to speak at the Ithaca Fest. I'm very invested in the Ithaca community. I really like the project, so it's a double pleasure to speak here. So today I'm going to annoy you with some very hand-waved conjectures about how to organize open cybernetic systems in triple categories, which are like very high technologies, even just define them. So let me first tell you what I mean by cybernetic system. I have a very vague definition of what cybernetic system is because there's many things that look cybernetic. So it's good, in my opinion, to have an open mind and then see where the limits actually arise. So what I mean is simply a system with a control mechanism on it and with like composition pattern instead of interaction. So usually they have, it's not just some kind of thermostat, but could be many thermostats. It could be a neural network. It could be agents in a game, stuff like this. And usually this is how you see represented a cybernetic system. So there's a feedback loop telling you how actions are converted into some kind of state of the system, of the like some action, and it's converted to some kind of state of the environment. And then you observe the environment again, and then you do this again all over by optimizing some things. The kind of cybernetics I do looks more like this, because I came from, let's say, categorical game theory, where this diagram is taken from. And the reason why I came from that area is because categorical cybernetics arise there. And therefore, what we're trying to do, like here at Strathclyde, but also other people around the world, is sort of like generalizing from that example after having noticed some similarities with, say, learning and control theory and like Markov decision processes and stuff like that. So for me, game theory is sort of a guiding example. And in general, the systems that we look at have, so let's say the string diagrams that we look at have this shape, right? So we're looking at, so the system is this composite of a blue and a green part. So the agents part is sort of sitting over some other process, a process which is interacting with the environment, which is usually a composite of other units that look like this. And what the agent is trying to do is to like steer and control the whatever dynamic is happening here by sending down an action and receiving back an observation, right? And indeed, like they have a very peculiar structure, which also entails a very peculiar composition pattern, because now you see that I can back. Is there a question? No. You can see that you can stack this like from any side, and this makes their behavior really interesting, really interesting. So categorical cybernetics, which is what I'm working on with other people here at Strathclyde, I will list them later, is trying to like understand the structure behind this. So what is the compositional structure of the cybernetic systems? How do we like write down models in the way that applied category theory taught us to do the thing? So compositionally, and by being very careful about the assumptions we're making and the structure that we actually use and exploit. And the goal, which is quite far from at the moment, is to like being able to like kind of resurrect cybernetics as a science which is more than just control theory, but can talk about like very different systems in a uniform manner. So yes, control plans, but also games, also learning, also reinforcement learning, and all this stuff does look like things that control other things. And so proving like theorems about universality of such systems, or things like the free energy principle for the systems, are very interesting and appetizing goals. And finally, something we want to do is, well, not me personally, but people I work with, surely, is to use these nice abstractions that we develop to write down better software. So software is more effective, more efficient, and more affable, which means more understandable. So better from a software engineering perspective, okay? Because using compositional abstractions makes writing big and large models for complex systems much easier. So as I said, controllers are the most important part of cybernetic systems. What, like, having that thing on top is what makes them different. And so in categorical cybernetics, we try to understand that part first with like the constraint that those things have to interface with something underneath, so the arena part. And this gives them the compositional structure, which is very interesting. And what we want to do as a first thing, at least for today in this talk, is to understanding their behavior. So given how a system actually, what a system actually is, what can we say about what it does, right? So as I said, we're being inspired by categorical game theory, categorical machine learning at the moment, but there's more work happening in this area. Anyway, so what I'm going to talk today. So I want to tell you how I think in the future we're going to talk about categorical cybernetics, and like how do we put like everything like everything here basically in a single unifying structure. And to do so, I'm going to extend David Jesmeyer's framework for categorical system theory, which is quite new, and I don't know if people are familiar with it. So the general idea of that framework, as far as I like, this is my belief, but maybe David will disagree, but I think this is pretty obvious from the mathematics, that it's the idea of studying system theory behaviorally, but in the functorial semantics way. So we're going to define something which encodes the specification of a certain class of systems, which you can think of as a syntax. We have like some target, like other class of systems of the same kind, but of a different attitude, that's going to, like, which we can think of as the behavior, so the semantics, and the functor is given the semantics, so telling us how a given system is going to behave in a, like, according to a certain notion of behavior. So since this is a big framework and it's quite new, I think most of the talk is actually going to be there, and is going to be only double categorical. So this might be good news for someone and bad news for others. But I hope it's going to be interesting. It surely is a magnificent mathematical theory. And then at the end, I'm going to tell you how I think the extension from like simple dynamical systems to cybernetic dynamical system works using indeed triple categories. So yeah, as I said, it's not going to be like a final answer to cybernetics. So like the full extension of this framework to cybernetic systems is still in the workings, but I think I have enough interesting things to show. And for the rest, I really hope that you guys, which are really knowledgeable in category theory, will help me understand better how to progress. Yeah, I'm going to thank a lot of people. I'm not going to read the names of everyone, but I've had many conversations the last 6 months. This is the stuff I've been mostly excited about in the last 6 months. So I talk about this with everyone, and I had wonderful feedbacks from people working in my group, people at Topos I visited in the last 2 weeks, and David Jesmeyer's, which have been very instrumental in improving my understanding of all these things. And then some conventions. So I'm going to talk a lot about double categories. To me, double category means weak double category. And I follow like Bob Perez and Mark Grande's convention. So vertical is weak, but I'm going to denote everything. I hope I didn't miss anything, but so what I call loose arrows, which compose weakly, are going to be vertical and have some kind of marking, and the other ones just look like arrows. And then these two double categories, which I call set and cat, are actually the double category of spans in set and double category of categories functors and profunctors, or what some people call profunctors, prof. And then, yeah, if you know the book that David wrote, it's not going to be exactly the same, but hopefully it will be understandable anyway. So let me begin with the meat, categorical system theory. So I think the framework is quite simple. Like if you look at it from above, it's just starting from the idea that processes organize in double categories. And once you have processes, you want to talk about stateful processes that we're going to call systems. And then the way you talk about them is by defining something like an index category, but double index category, which is a functor of this kind, and assigning a category of systems to every, assigning systems that are being reindexed by processes. And then we want to talk about behavior of these systems by studying maps between this kind of double index categories that like land in a specific observational theory or in some observational theory. I'm going to clarify everything, okay? But this is like the bird's eye view. So let's start with process theory. A process theory to me is just a double category, but with an attitude, so with a way to like interpret what we do and what we define. So objects in a double category called process theory are, we think of boundaries or interfaces between processes. Vertical morphisms are processes. Horizontal morphisms are instead maps of boundaries. I'm going to clarify what I mean here. And squares are maps of processes. Okay, so this is how a generic square looks. It just looks like a generic square in a double category. And of course, like some people may object, this is a very, very like narrow definition in a sense, like very large, possibly better. So like many people are like, oh, process theories have to have some kind of monoidal product. I call them concurrent process theories. And I think this is like the bare minimum to do process theory. And then you add like all sorts of structure on top of it, depending on like what kind of processes do you like. I really like concurrent process theory, of course, but I don't think they're like the only possible process theories around. But anyway, so we have a double category. What do I mean by this like thing? Maps of boundaries and maps of processes. So these are two different kind of maps. They're not the same maps as processes, right? So I think of boundaries as kind of like wires. So there are things that system like gets plugged to, and this is how like signals go around. But they are static, right? And there's nothing happening in a wire, and there's nothing happening in a map of wires, so a map of boundaries. Okay, so a map of boundaries is just a way to say, okay, I have like two wires and they transmit stuff in a similar way, and I can map between these two ways. So I tell you how a given boundary can be interpreted as another boundary. But in this interpretation, nothing happens, okay? It's just like in the model. Whereas processes are dynamical. So what's described by the process is actually something that happened. So it still links to wires, but now there's a linking that means like I receive a wire, something happens, another wire goes out with different stuff. And of course, maps of processes are equally static. So these are going to be, so map of process is a square, and this is something that maps the execution, the dynamics of the process and the dynamics of this other one. And it's itself mediated by some mapping we have on the boundaries of the processes, right? So this is it. So let's start with one of the most important examples for what I do and for the rest of the talk, which is the process theory of lenses. So in the process theory of lenses, boundaries are simply pairs of sets, and the processes, which encode the dynamics, are these kind of bidirectional morphisms that are called lenses indeed. Oh, sorry, this should have been A plus, B plus, of course. So the plus part or the bottom part, you should think of like actions. So P is something that takes an A and executes an action B, okay, by like processing something. And then the upper part, which is also labeled by minuses or sharps for the morphisms, is instead something like a reaction. Okay, so I get an A, I reply with a B, and then on the other side, someone replies with a B minus. I still remember that I received an A. So when I answer to whomever asked me a question by telling me A, I reply A minus. I remember what I did in the interaction. So I remember the question in a sense. Okay, so they have this characteristic back and forth shape. Okay. And with lenses, we also consider charts. So these are going to be our vertical morphisms processes. Horizontal morphisms are charts, which look a lot alike. But if you notice, like H flat goes in the opposite direction as P sharp, okay? So this is, remember, static map of boundaries. So it's a way to recognize how like questions and answers of a given kind can be mapped to questions and answers of another kind. But there's nothing happening there. There's no like question, like Q&A. Okay, this is not happening. And finally, squares. What are squares are a bit messy when you write everything down, but it's really simple conceptually. So you see so all of these maps have two parts, and what you can do is say, well, let's look at the like downstairs part, so the one with sign plus. I want that square to commute, and this is the first condition. So just saying, if I do an action here and then I map it to a result here, is the same thing as if I use the mapping first and then I did my dynamic on the other side. And then the second part is just a bit messy to look at because like we have this second argument here, but more or less the same. It's telling me that if I do P sharp and then H flat is the same thing as doing K flat and then Q sharp. Okay, which is again telling me that this like processes commute with the maps. Okay, so notice there's nothing in the square, so it's just like a commutativity condition, which means that for any given arrangement of cells around the square, there is possibly only one square. And this is just because like this theory is like this, but it doesn't have to be like this. For example, like one can look at variations of this theory. And the first I had in mind was, oh, let's make this non-deterministic. It's really easy. We just stuck a P in the output of the like upstairs part of both lenses and charts. And this P is the power set monad. So it's just like, okay, I don't give you a set of answers. Sorry, I don't give you an answer. I give you a set of possible answers. And now we weaken the commutativity condition. So it's the same condition for the square, but you see here there's a subset, which means that we just require that, like when you go down here, this path here, and then you go up here, then whatever did here is still good for this, but there might be more stuff involved. So now, in a sense, the square is still, there's still only one square if there is a square, but there's already more meat there, okay? Like one can imagine like labeling the square with how much you want this to actually coincide. And if you go with other types of non-determinism, that's like very compelling to do. Another lens example, there's a lot of zoo with lenses, but this is like things that I need. So I think this is more interesting in a sense, because it's more refined. So dependent lenses are like lenses, but the boundaries have a more nice structure in which the type A minus of like possible reactions is dependent over the type A plus of possible actions. So this dependency is encoded in an index category. So this is a very like general dependent type theory. It's just an index category. It's just like the suggestion of a type theory in a sense. And All right, so now it means that we have this dependency, and accordingly, like P sharp and H flat, which are like the upstairs part of a lens of our chart, are going to be mapped depending on that. So we have to, so given an A plus, then I'm gonna get a reaction from like whomever I answer to over that answer I gave, and I'm gonna give back a reaction over that there should be a plus over that A plus to someone else. So this is saying that the type of answers to a given question depends on the given question, okay? And so does the dynamic. So it respects this thing. So I think the example I mostly care about for my application of this stuff is like the most, let's say the least non-trivial one is given by the index category of submersions for smooth manifolds. So this is like a slice category, a slice indexing. Okay, so the most simple possible. But since in smooth manifolds, not every pullback exists, when we take the slice, we only look at those maps in the slice that are given by submersions. And submersions have the property of being the maps of manifolds that pull back. Okay, so in a sense, they're like display maps for some notion of dependency in the category of smooth manifolds. But like, this is all to say, like, I want at some point to talk about the type of tangent vectors over a manifold, right? The tangent bundle is given by a submersion, and the tangent bundle is non-trivial usually. So I really need to remember where I am to know the type of tangent vectors at that point, right? So when we do lenses for this data, we get this lens sub, which is the process theory of smooth processes, in a sense, differential processes. Now, the other very important class of process theories is given by double categories of spans that we interpret here as being observational theories. So the processes that we talk about here, which are given by spans, like do not actually have any dynamical content. They just remember they have a set of states, and given a set of states, I have two maps that project the observations that I make about that state on the boundaries of the process. So we loosely think as A of being like the input and B of being like the output. And so for any given state, there is like an input-output relation between the two, but we don't really remember how this input-output happens, right? So it just make observations about things. And so in a sense, observational theories are the archetypal form of behavioral theories. And in particular, when C is set, spans of sets are the target of all home functors from double categories, right? This is because when I map into a horizontal arrow, what I get is a span. I map horizontally, sorry. So we can see that any process theory can be like mapped into the behavioral process theory by like fixing some kind of some A, which is like area used to probe other boundaries and look at all possible observations from that boundary to other boundary, right? And then we're going to see that this can be promoted to a full-blown map of like the map processes to like spans that forget what happened to what happens in the process, and they only like remember the input-output relation of the process. So now I've been talking about processes all this time, but this is called categorical system theory. What is going on? The point is that there is a subtle difference between processes and systems. So processes, as I said, are like dynamical things that happen, do things, but systems are a bit more like stateful. That's it. So we want to talk about processes that have some kind of like memory, so they stay the same, and then they interact with the rest of the world using processes that mediate interaction. So I'm giving you some example. So I think the easiest one is like Moore machines. So by the way, do you see this little window, like this zoom window here? Does it cover the slides? Okay, fine.
No, we don't see it.
Good. Then I'm not going to worry about it. So a Moore machine is a lens where we fix the left boundary to be like a pair of sets, which is the same set. and it's the set of states of this finite state machine. Okay, so now the lens is going to give me an output for any given state I'm in, and if I'm in a state and I receive an input, I'm going to go to, right? So you see the statefulness now. It's not just an interaction back and forth. Is I have my state, and then we interact through the outer boundary, but this state is thought of as the same, even if formally these two S's are not the same. Another example, so I told you about lenses from smooth manifolds and submersions. Like if I look at like a system in that process theory, then I get something like this. So I have like a lens again that has an observable on a given state space or a given manifold of states. So the state space S, and this exposes some kind of observable. And then I have given an input, so imagine some kind of interaction happening here. Yeah, an input and a state I'm in, I'm gonna date a tangent vector at the point I am, which is giving me the update rule, basically, okay? But now this update is not a new state as in the Moore machine, but it's a tangent direction. So this is telling me how should I go in the next infinitesimal instant. And then finally, like for observational theories, then a system is just like a map telling me like for a state I am in, what will you observe out of it? So a system theory, so crucially systems can be composed along processes, rewired along that, and can be compared with other systems using interfaces, like using their states, whatever. So a system theory is a doubly indexed category over a given process theory P with some attitude again. So what I mean by doubly indexed category is a normal X double functor of this shape. So there are some like type issues here, but I think it's quite understandable what I mean. Let's see by like what I mean by attitude. So for any given interface A, I get a category of systems over that interface, and which are the objects, and maps are like simulations, so ways to see a system as being another system. Then processes act functorially by rewiring. So I have a system over A, I have a process linking A and B, now I get a system over B. Maps of boundaries act profunctorially by telling me, and so if I have system H, then, and I have a system over A and a system over C, then I interpret this, the set that this profunctor gives me as the possible ways that I can look at A, sorry, as S, sorry, the possible ways that I can map S into R with the mapping on the interfaces mediated by H. And finally, maps of processes give squares in the category of, in the double category of profunctors and functors, so they have the shape, which are given basically by extension. So I have a way to map systems here. I have a way to map extensions of systems. I extend the way that I was mapping the two systems across this.
Matteo, can I ask a question? So
sure,
for example, sure. I would like to see lenses over set as one of those guys. In what sense is it so?
What do you mean by those guys?
How did you call them? Go a couple of slides before. How did you call it? A system theory. I would like to see the two categories of lenses as a system theory.
Right.
Because from what I understand, it should be.
So the lenses, together with charts and those squares, organize in a process theory. And now I'm going to tell you about Moore machines, which are the notion of systems associated to lenses. So like a stateful lens is a Moore machine. Mm-hmm. So lenses form this double category, which indexes Moore machines. Am I answering your question?
Mm-hmm. Yeah, I think so. Yes, thank you.
Okay. We can go more in detail later if you want. So as I said, Moore machines are a system theory over lenses. So given an interface, I get like the category of lenses with that given interface on the right, and with a left boundary which has this shape. Okay, so it's a set of states both in the like covariant and the contravariant part. And then maps are squares in lenses whose top boundary has this special shape. So it's not just any chart, it's a chart which is the same in both parts. Okay, which again like testifies that we're thinking of this as really as one object. And the way, I'm gonna skip this, sorry. And the way like this assistant theory is that if I have a lens mapping here, I can just compose them with the lens of the Moore machine, and this gives me a functor. If I have two systems, so two Moore machines over two different boundaries, and you give me a chart between these boundaries, then I can look at the set of possible squares that have these three prescribed sides, so the two systems and the chart. And this is like the ways to map one Moore machine to the other Moore machine, mediated by this map on the interfaces, but like free on the states. And so, yeah, let me give just an example of this. So there is a system which is like called clock. So it's just a clock, which is a Moore machine with state space given by the natural numbers, which we think of as a timeline. And it outputs its own, like it outputs the time, it's a clock. And the update rule for a clock is go like in the next time step, go to the next time step. Okay, just update this. Now, if you have a chart from the boundary of the clock, so just one end, to any other boundary, the associated profunctor, when we evaluate it at the clock system and at another given system, so another given Moore machine, gives me the set of squares which have this shape. And the commutativity condition tells me basically that the map I give here from natural numbers to states is a trajectory of the machine. So is a set of states that the machine will go through when I feed it the given inputs here at every time step n. And I'm going to witness the given outputs basically out of it. Okay. And squares go to squares. It's just stacking squares. It's not very important. So this defines a type theory, as I said. So assistant theory, as I said, there's many different assistant theory you can associate with like different flavor of lenses. And another very important assistant theory is the theory of observation systems. As I told you before, an observational system is just a map from a space of states to a set of observations we can make about the state. So it's what you usually call an observable. So an observable system is just an observable. And these things rewire along spans. So you can think of spans as being like synchronization conditions. Like I want to witness, if I have a system that gives me a relation between I and J, then this is going to induce a relation between S and whatever happens in J. And the way this, so what happens basically, if you give me a system, so an observable over I, then I can pull it back and then push it forward along the legs of the span and get an observable over J. So I can define a profunctor as before. So given two observables, I look at this map and the possible squares between them mediated by a given map in the horizontal, like in the bottom boundary. Also in squares, I can just like do the obvious thing. And then I get a bunch of system theories that are all like callable system theories of observable systems. In particular, there's going to be a very important one, which is the one we get when we like instantiate C as being sets, in which case the assignment is basically that of families. So if you give me a set, the observables over that set are just like sets over I, which we know is isomorphic to set index by I. So in a sense, we invert the relationship here. We say, for any given observation, I'm going to give you the set of states that can produce that observation. All right. And then like, again, it's going to be acting on, like spans are going to act like pull push, and then maps of sets are going to act like profunctors that give me the set of maps between these index sets that like are compatible with that, and blah, blah, blah. So this has a special role because it's sort of like the codomain of the home functor of a given system theory. So what I mean is this: if you choose a system, so if you have a system theory SIS, okay, and you choose a system S over any of the fibers of SIS, then you can look at a triangle like this. So if S is over I, then there is the covariant horizontal home functor of P, starting from going out from I, which is going to give me for every interface J, it's going to give me a set of like maps from I to J, the horizontal direction, so maps of boundaries, so the static ones. So you can think of observations of J from the standpoint of I, okay? And then here we hit set, and then obs, which is going to give me like observables over that set, is going to map this to the category of sets indexed by all these possible ways to look at J from I. On the other side, I have, so if I chose a J here, I get systems over J. And this triangle is filled by a nature transformation between, that's going to map cis J to sets indexed by maps from I to J. And the way this acts is by reusing basically cis. Okay, this is imagining a home functor. So now you chose a system S over I. I'm giving you a system T over J and a map from I to J. So we know there is a profunctor associated to H, which is this map I gave you, that's going to tell me how the system S that I chose initially, so this is whose home functor we're looking at, is going to map into T, mediated by this map H between the interfaces. Okay, so this is really like the home functor from S to like, sorry, the home functor of S, the covariant home functor, okay? And in categorical system theory, these are called co-representable behaviors of type S, okay? In the sense that we can think of this as picking out all the possible ways that we can map S into any other system. And within there are systems that can be considered like walking kind of behavior. So for example, within the clock system is the walking trajectory in the system theory of Moore machines. So this means that the co-representable behavior associated to the clock system is the behavior functor that like picks out for any given system the trajectories of that system. And most importantly, it gives me all this compositional structure, how these trajectories change when we reindex systems, when we map systems, and so on. So to give you something concrete to look at, so let's go back to our Moore machines. So the system theory of our lenses, and I take the super simple Moore machine, which is the Moore machine that does nothing, has no states, no input output, just sits still. Okay, so we can consider this to be like the walking fixed point or the walking steady state, right? It's a thing that does nothing. So there was a steady state is. So we expect that when we look at the functor, so it's like this triangle that we obtain by looking at maps out of fixed, we're gonna get something that like represents the behaviors of steady state, okay, the steady state behaviors of a given system. And indeed, this is what happens. If you give me a Moore machine T, then, and you give me a chart from like into the interface of T, and from the interface of the Moore machine, this is going to just pick like an input and an output. And then this chart will determine a profunctor that given like fixed and T will give me all the squares from fixed to T with bottom boundary given by this choice of chart. So this square is going to tell me like, sorry, this S should be a T. Now I shouldn't have renamed them. Anyway, so this is giving me all the, this is the set of all states of T, which are going to make this square commute. And if you look at the commutativity condition, this is basically saying that given the input that we chose here for the chart, then if you're in state t, we're going to still be in state t. And then we know we're going to observe O from that state. Okay, so you see how this is the walking steady state. It's peaking out for any given t and any given map, like choice of observation I want to make in the boundary. It's picking out the set of steady states that are compatible with the observations. Okay, and most importantly, like this, like once we fix the system fix, then we get a very, sorry, this shouldn't have been viewed. This should have been the profunctor, sorry, the home functor from 1-1. But anyway, this gives me this co-representable map here, which are gonna peak or automatically like give me all this kind of structure of like what fixed point behaviors look like, right? So it's not just giving me the set of fixed points for any given system, it's also telling me how they like change when I change the system. So if I reindex it, if I compare with other system. And so this is normally like only lax functorial in the, so sorry, I should be more precise. This map here, filling the triangle, which is a vertical nature transformation, is only a lax transformation usually, which is a way to say, like lax with respect to vertical maps, which is a way to say that if you give me a system and you look at its behaviors and then you rewire the system, so you like compose it with other things, then you get things that are, so you get some behaviors of the new rewired systems. But in general, when you first like rewire the system and then you look at behaviors, you're gonna see more things. Okay, so this is the whole emergent effects thing, right? When you compose systems, like there's the behaviors composed, but the composite will have behaviors that you couldn't just determine from the behaviors of the parts. But in David Jesmeyer's book, where all this is like worked out in much more detail than here, like he proves that like in many cases, if this system we put here has like a very blend property, then this map is actually invertible. So it means that we have a very strong compositional property for behaviors of that type. Okay, so we have all this machinery, and then we just have to check like if you want to like talk about behaviors of specific kind in a like and the way they compose, we can get very strong guarantees just by looking at first if the behaviors we're interested in are co-representable. So if there is a walking kind of that behavior, and second, if that system satisfies like this condition, which is very easy. And so this is great.
Sorry, one question. So is it correct to say that if this map is an ISO, then it means that there are no emergent behaviors in
Correct.
the system? Like compositionality is kind of algebraic, let me call it this way.
Correct.
But then you said that a lot of system, like you said that this is a weak condition, but it should be a very strong condition because most of the systems should have emergent behaviors.
Yeah, so the condition is the following, I'm going to tell you. So let me go back to the definition of a Moore machine. So, okay, this is Moore machines. So suppose we want to, like, we fix S and we want to talk about behaviors of type S, then it's enough that S completely exposes its state, which means that output has to be an isomorphism, a bijection, okay? So this is telling me that if we know exactly how these behaviors came into existence in the first place, because we know everything about, like we expose everything about the dynamics of the system that generates them, then there are no surprises when we compose them. Or at least like given this framework, we can completely like account for this, like the new emergent effects. That's the way you should understand that. If output is not ISO, so it hides information, then it means that when we map stuff, we don't remember things. And then when we compose, different behaviors, then these things that we didn't remember might come to haunt us. Very high level explanation.
Can I ask something which is gonna sound extremely hand-wavy?
Sure.
So, in a sense, when we think of emergent behavior, one place where they should exist are dynamics in the sense of topological dynamics. So there is where, in a sense, there are a lot of emergent behaviors which are not locally seeable. Is there any way that this framework can actually talk about topological dynamics and actually tell us something about the emerging behavior of topological dynamics, or not?
So I think in principle, yes. If topological dynamics is you have a topological space and an endomorphism of it, correct?
For today, yes. For today, yes.
So you can set up a theory of topological systems or topological dynamical systems and see what you get from that. It's not going to be true that every behavior you're interested in is going to be completely compositional. But this gives you a way to have many behaviors you're interested in to actually have a compositional description. And like the trick is here in this map. So you have a nature transformation here that depends on the rewiring you chose. So this is why like this is not surprising in a sense, because usually emergent effects are surprising because you have behaviors of A, behaviors of B, and then you put them together, well, you put together A and B, and then they have new behaviors. But this wouldn't be surprising if you remember the way you put together A and B, and if you knew very well what A and B are doing, right? So by remembering the way we put together things, we can like do the same thing to behaviors and compose them in a way that is completely exhaustive in many cases.
Thank you. I take this as an answer, sorry.
Where am I? Okay, behaviors. So we can say that in general, if you have a given theory of systems, then by looking at this kind of maps into the theory of like the observational theory, so the theory of things that I can observe and nothing else, then we're studying a notion of behavior for this notion of system. Okay, this could be anything. And when we manage to define this, we're going to have like some compositional properties. Like we know that how to index stuff. We know that the composites of the parts are going to give me composites of the behaviors of the parts are going to give me behaviors of the composite. And moreover, so we can study like behavior in this way, but it's nice to observe that like if I manage to recognize that my behavior is co-representable, so I can find a system that is like the walking behavior of the type, then all this composition structure is just given to me because like there's the general result. And moreover, like one can try to characterize like stronger properties about this notion of behavior depending on the system that embodies it, or just if I have just this transformation just to understand what this behavior is. So in a sense, we have now a good way to talk about behavior, in my opinion, and with lots of structure just encoded there, which is good if you want to study behaviors of systems. Unfortunately, I don't have like lots of surprising results to show you. This is a very young framework. But there are some interesting things. I think I can convince you something like this is like an interesting thing when I come now to categorical cybernetics. So are there any other questions about the first part? I know I'm nearing the end.
Maybe one thing. So technically now we're going over time. We still have time, but so you're going into question time. So you can still...
I consider that has been interrupted, so some minutes to recover.
Yeah, that's true. That's true. That's some few minutes. All right. Very good.
Okay, we'll like cut the mustard here. Wait, let me tell you like the punchline at least. So as I said, I'm interested in systems that have a bit more structure than the ones we've seen so far. So again, I will propose it as colorful pictures. So usually partition in at least two parts. So we can safely ignore the red part because this is like when we close the system. Well, in general, we don't close systems. So we just look at processes which have like some kind of dynamic along which we compose them. And then over them, over any given process, they're like a pilot, a controller. Okay. So there's a nascent field of categorical cybernetics, which like has a bunch of papers out. But the two things that like everybody that works on this agrees on is like this mereological structure. So this way that cybernetic processes partition into something that is the controllable process and something that is the control. And the fact that the way, like a good way to model this is by using two-dimensional categories. So by categories so far, where like we imagine like the first dimension to be just like the controlled processes. So we don't know anything about what's inside. And then when we open up the second dimension, we can see the control dynamics happening there. So it's like a process theory nested inside another process theory, okay? So there is the process theory of blue things that is nested inside the process theory of each of the green things. And the way I like to model this kind of by category, so this kind of process is by taking literally that a control is sort of like parameterizing the behavior or the dynamics of the process it's controlling. So there is an extra port for any, like given a process from X to Y has an extra port, which is where actions of the controller come from. That gives rise to the second dimension, because now we can build a bicategory from any monoidal category C, where like objects are the same. One cells are given by indeed parametric morphism, so a choice of parameter and a map from X to Y with parameter P. And then two morphisms are just, so this should have been, sorry, QF and PG. Phi is a map from Q to P that makes this triangle commute, okay? So it's a map between the parameters that has to be like compatible with the rest of the dynamics. So you see now it's like quite inviting the situation. We can, with very little effort, promote parse to be a double category. A double category, which I'm not going to interpret as a process theory, it's just a double category, was vertical morphisms are parametric processes and horizontal morphisms are non-parametric processes, okay? And like a two cell is like the triangle we've seen before, but now we detrivialize this, also these two boundaries, okay, are non-trivial now. And this is not just a double category, it's a company or an F category or whatever you call a double category, which has companions for every vertical arrow, in the sense that, I should have said horizontal here, I'm sorry. What I want to say is that non-parametric morphisms can always be like bended down by assigning them the trivial parameter, okay? And this structure brings together many different approaches to like categorical cybernetics and like things that look like those approaches, which is very nice. So one is the paraconstruction I told you about. Toby's Might has its own like variation on that. There's span, which can be interpreted as sort of para construction. There are other things that people do in polyspace, so like with polynomial functors and so on. So this all comes together in this abstract structure. But as I told you, I'm not interpreting this as a process theory, right? I'm interpreting this as a double category, but it's all processes, right? It's processes here, it's processes down, it's processes inside. And a process theory really needs some notion of like static map, okay? Map that I can use to like compare processes. So this is where the third dimension comes from. So I want to give you now the definition of cybernetic process theory, and then I'm satisfied with my talk. So a cybernetic process theory is again a category with attitude, but now is a triple category. Okay, so a triple category is, imagine a double category, but instead of looking at squares, you look at cubes. That's, I think, the easiest way to think about it. Of course, it's a bit more complex than this, but in first approximation is a category with 3 types of one cells. So in the case of cybernetic process theory, we interpret maps in this direction, which is the transversal directions, as maps of boundaries. So the transversal direction is a strict direction, and this is strict as was maps of so also maps of boundaries was strict in normal process theory, so we keep that. But now we have 2 loose or weak directions. Okay, the vertical one, which is processes, so without any sort of control dynamics, and the horizontal ones are controllable processes, so processes that expect to have some kind of control happening on top of them. And then, since we have 3 types of one cells, we have also 3 types of 2 cells, okay, based on every possible combination. So basal 2 cells, are this one. So I'm using the standard terminology, but I think they should be called like frontal 2 cells. So these squares here are the squares we've seen before from the double category called para. Okay, so they have processes, and they map controllable processes with something that is actually another process. So it's a control inside telling me how to reduce the controllability problem of this process on the bottom to the controllability problem of the process on the top. And then we have on the vertical direction, so this 2 cell here is a map of processes of the kind we've seen for process theory. So we have a process, maps of boundaries, and this is mapping a process to the other mediated by these maps. And on the bottom, horizontal 2 cells, so this one, these are new, and these go from controllable processes still mediated by maps of boundaries, but now they have also like this extra controllability thing to take care of. Finally, cubes, and I apologize because here the perspective is a bit off. Cubes are like maps of control processes. So control processes are here. So these vertical maps in the basal 2 cells. And you see now like you have 6 2 cells organized into a cube, but this one in the back and this one in the front are control processes. And the maps on around it are telling me like how to map all the things that the control process interact with. Okay, so these are the processes on the side, and most importantly, like these 2 ways of mapping the controllable. So the processes that the control process is controlling. It's a bit of a mouthful. Okay, so maybe looking at an example is going to be a bit clearer. I apologize if I'm going over time. So let's look at lenses. We still have like charts and lenses, but now we add the horizontal dimension, which is given by parametric lenses. So these are still lenses, and I'm putting like the parameter there. And you see that what happens is now, okay, we have the same vertical 2 cells as before, but now when I look at horizontal 2 cells, which are mapping controllable processes mediated by the same charts we had before, this means that now we have an extra data here that tells me how the boundary where the control is going to stick at is mapped to the other boundary. Okay, so we have an extra boundary in parametric lenses, and we have an extra notion of how to map this boundary. And basic 2 cells are just like these cells in para, which we can think of as just sticking this lens over this parameter at the bottom and giving me what's at the top. And then a cube is going to be something like this. So it's an arrangement of various things, but you see like the blue thing is what's important. A cube is just going to be a square of the kind we have in lens, the double category of lens processes, where we map this control process to this control process mediated by all these maps in the edges of the cube that tell me how like the boundary of the control processes are mapped. Well, now we have this blue map that tells me how the map in the, like how the control boundaries are mapped. And this is linked to other things. I just want to mention this, that like, this is an interesting like way to do things, because you can prove that you can arrange, if you give me a game expressed as a parametric lens, with on top a control process, which is the dynamic of the players. So you cannot for like argmax kind of payoff function. Then fixed point behaviors, like which are analogous to the one we see in the first part of the talk, are going to, of this game as system, are going to be Nash equilibria, okay? So in a sense, we substantiate the claim that Nash equilibria are equilibria by saying they are fixed points of this system in a certain sense, okay? And as I said before, like, this is all nice because if we manage to, like, so we have now a system that represents Nash equilibria. If we manage to like define something like the co-representable behavior, Fanter, blah, 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 then we have all this nice like compositionality formula. So everything like falls nicely without having to define compositionality for Nash equilibria or for any other notion of like solution concept we mean for games. And to do so, I should tell you like what is a cybernetic system theory, what is the cybernetic theory of observational processes and systems, and what is a behavior functor between the two. But these are answers I don't have yet, and have various speculations that I'm gonna like save you. Thanks for your attention. Of course, if you're interested in the speculations, you can ask me now.
Okay, very good. Thank you so much for the talk. There's a lot of virtual applauses if you see the participants and the videos. And all right, does anybody have any additional questions? Feel free to unmute yourself.
Oh, sorry.
I have one question. So
go ahead.
So you said you have ideas to understand the treatment of Nash equilibria in game theory, and you have ideas about it. I understand it's not finished, but you have ideas. Mm-hmm. So what about other equilibria? For example, Pareto equilibrium and all these other variations of equilibria. Do you, like, would this also fit in the general framework or not?
So the problem with game theory is that solution concepts, so these are the notions of equilibria. Okay, let me take this a step before that. So in game theory, classical game theory, there is not much like attention to the way that like the dynamics of the game is distinct from the dynamics of the player. Let's say usually game theory is not framed as a control problem. We can say it like this, okay? So you have like a utility function and players, not better specified, and then you can like tell me arbitrary things about the situation. And so when you analyze more carefully all these solution concepts, like they're not as like uniform as one might expect. They're not like just little variation of the same thing. So Nash equilibria are just incredibly natural. So they happen because like when you stack these things, they just like work like that. But things like, for example, sub-perfect equilibrium, which is this notion that we are in a Nash equilibrium, but if you threaten me with something which is non-credible, for example, I'm gonna nuke you if you do this, but then you know that if you're gonna nuke me, then I'm gonna nuke you harder. So you never actually want to nuke me because you know that when we are actually in that part of the game, that's gonna be an inconvenient move for you. So this is a stronger notion of Nash equilibrium, right? But this stronger notion like is super tied to the way you specify the game. And it's not something that has the same nice property as Nash equilibrium. In particular, it's not something you can just observe. It's something you can like make players to play, okay? So in a sense, I can tell you sub-imperfect equilibria are still equilibria, so still fixed points, but for players which are arranged in a different manner, okay? So players, I'm gonna arrange players in a way that they now compute the subgame perfect equilibrium instead of the Nash equilibrium. Or same, I can arrange players in such a way that they compute the Pareto equilibrium, right? But this is not a property of, like, it's not a kind of behavior anymore. It's a kind of dynamics. And the kind of behavior is still the same. It's not a fixed point. So that's a bit disappointing there. But this is still stuff like I'm thinking about. So
yeah.
it might be that
are you hinting that in a sense, given a game, there is another game such that it's the Pareto equilibrium of the second game is actually the Nash equilibrium. Sorry, the Nash equilibrium of the second game is actually the Pareto equilibrium of the first.
Yeah, not every game, but most games, yes.
Interesting. Thank you.
Very good. Thank you. Are there any more questions? Well, I have one. I'm a little bit curious about this conjectural material that you mentioned at the very end. Can you tell a little bit about that?
Yeah, so I left you with like 3 things to do to like finish the talk in a sense, right? Which is, okay, I told you what cybernetic process theories are, which is triple categories with an attitude, but I didn't tell you what a system theory is. And then I didn't tell you what is the observational, like what is the cybernetic system theory of observational processes and systems that I can use as like my theory of behavior. And so the second question is really answered. So like in a sense, at least the theory of controllable observational processes is decided by the fact that if we want to imagine this as being like things, like if we want to imagine this as being like the codomain of things that are like representable home functors, then I have to look at home functors. And when I look at home functors of triple categories, then these land in spans of sets. So it is, what if you do span of sets another time? And then you get like this category of funny cubes like this. And like the transversal home functor from a given triple category, so a given cybernetic process theory, lands in this triple category. So this gives me like what it means to be a behavior here. But unfortunately, the 2 other questions are much harder because I don't know the answer to the first. Okay. So to understand what I'd want to do is, so if you give me a controllable process, which is not an object in the category of cybernetic system, like in a triple category cybernetic processes, but it's a horizontal cell. So suppose now you just like give me those as objects, then I know what to do. If you give me a controllable process, then I want to map it to a category of control processes over it. Okay. So in a sense, we do the same things we did before. Okay. Now there's going to be like a series of vertical cells that are plugged in over any given horizontal one cell. And those I want to, like, processes of a specific kind, which are here, those are one I want to call control systems. Those I want to call systems. But it's hard to express this structure. It's a bit hard. I just know it, like, it's probably some kind of like, I don't even know the codomain of this functor. Like, probably going to be some kind of bimodules in cat. I want control processes to have this kind of like action. So you can think of this as an enrichment, probably, where you say, oh, there are like systems over I. Given I and j, there is like a home object, which are systems over I and j and decompose. I don't really know. But if you have any idea how to like make this functor into an actual thing, then I would be very glad to hear it.
I see. Okay. Are there any more questions? Seems not. So let's thank our speaker again. And let's also stop the recording.